Rolling on in section 5.5, we're talking today natural logs and the exponential functions. So we've talked e's way back when. Now we're throwing in our natural logs to our problems. So example 1 here, f of x equals e to the x natural log of the square root of x minus 2. What am I going to do? Well, the first thing I'm going to do is, I don't like that natural log of the square root. I'm going to change that radical to the 1/2 power. And remember, I can take that 1/2 power and I can bring it to the front of my natural log, which in this case is being multiplied to e to the x. So I can bring it all the way to the front and kind of get rid of it for a while. So I can write this as 1/2 e to the x natural logs of x minus 2. Now I can think about my derivative. Well, I have x's in two different parts here, don't I? I have e to the x times that natural log of x minus 2. So I'm going to have a product rule to work with. This 1/2, that's a constant, so I can kind of just let that hang out there and multiply it in at the end. So how do I find the derivative here? I got a product rule, don't I? So I'm going to have e to the x, and to that we're going to multiply by the derivative of the natural log of x minus 2, which is 1 over x minus 2. And to that we're going to add the natural log of x minus 2, and then derivative e to the x, which is, of course, e to the x. What can we do with this? If it's multiple choice, we're going to have to work it to the answer. If it's extended response, we're pretty much going to leave this unless it tells us to factor out any common factors or find a common denominator. Multiple choice wise, though, is kind of where I'm going to attack this. Multiple choice, they're going to factor out an e to the x. Notice we have e to the x in each of our terms. So I'm going to go ahead and do that. So we have 1/2 e to the x. And then we have left over 1 over x minus 2 plus the natural log of x minus 2. And this is probably where we would leave it. I don't know if we need parentheses or brackets there. But we could also find a common denominator. So that would be 1/2 e to the x times 1 plus the quantity of x minus 2, natural logs of x minus 2, over x minus 2. Getting a little cramped in there. So that would be a common denominator. And then what we could do actually with that would be bring this 1/2, since we have a denominator of 2 there, and bring that with the x minus 2. So we could see this as e to the x times that 1 plus x minus 2, natural log of x minus 2. Again, I'm getting cramped. I need to give my stuff enough space. And then 2 times x minus 2 in our denominator. So again, that's a natural log of x minus 2 in here. Right? And that would be maybe a nice clean answer if you want to think cleanly about it there. We'll see it again in example 2 here. We have e to the 3x times the natural log of x plus 2. So very similar to what we had up here. So our first derivative, I'll try to maybe space this out a little better. We'd have a product rule. So we'd have e to the 3x times 1 over x plus 2. And then to that we'd have the natural log of x plus 2. Derivative of e to the 3x. Recall derivatives of e to an exponent, that's not a single variable. We take the derivative of the exponent, which is 3. And e to that same exponent. And then to clean this up, again, there's not a lot we're going to do to clean it up. Just get into maybe a multiple choice version. We have e to the 3x in common with both of our terms. So we can factor that out. And that's going to leave us with 1 over x plus 2 plus 3 natural logs of x plus 2. And then from there we could find a common denominator as well. Again, it just kind of depends on who's writing the test quiz to what you're going to see. So we'd have 3 times x plus 2, natural logs of x plus 2, and that's all going to be over that common denominator of x plus 2. Now, I could get nasty and ugly and miserable because remember up here when we had this 1/2 and we brought it all the way to the front of that e to the x? Notice here we have a 3 being multiplied here times the natural log of something. So some professors, you may see, brings this 3 back up to the exponent of that x plus 2. I generally don't, but it's something that could happen in a multiple choice test. So just watch for it. I guess just a couple more examples. I'm just kind of get you into the swing of things again. We can see a natural log of x within a quotient rule. So our first derivative is going to be x to the third. Derivative of natural log of x is 1 over x minus natural log of x, derivative of the denominator, 3x squared, over x to the third squared, which is x to the sixth. Remember, exponent to exponent, we multiply. Cleaning this up, we have our x squared minus 3x squared natural logs of x over x to the sixth. Again, each of my terms have x squared in them, so I can go ahead and factor out x squared out of the numerator, cancel it with our denominator, and that leaves us with 1 minus 3 natural logs of x divided by x to the fourth. And again, since we have this 3 as being a coefficient of a natural log, we could see that as an exponent. So 1 minus the natural log of x to the third over x to the fourth. Finally, a natural log of a natural log. Ooh, how juicy is that? So how do we find the derivative of natural logs? Well, to find the derivative of natural log, we take the derivative of the inside of the natural log, or what we take the natural log of, divided by what we took the natural log of. So, well, what do we do with that? Well, the first thing I would do with this would be to change it to the natural log of 2 natural logs of x. That kind of makes sense, doesn't it? And then from there, this is 2 times the natural log of x. So I would actually go ahead and break this up using my natural log rules. So I have the natural log of 2 plus the natural log of the natural log of x. Why do I do that? Well, because I know the derivative of natural log of 2. Natural log of 2 is a number. It's a constant. So the derivative of natural log of any number is going to be 0, just like any constant's derivative is 0. So I just have the natural log of the natural log of x. So what do I do? Well, I take the derivative of the natural log of x, which is 1 over x. I'm going to divide that by that function, which is the natural log of x. So I'm going to end up with 1 over x natural logs of x. Now you may be asking yourself, well, what if I don't remember to do that? What happens with that? Well, I could have then taken the derivative of the natural log of x squared. Derivative of natural log of x squared, well, I take the derivative of that, which is 2x over x squared, and then divide it by the function, natural log of x squared. If that makes, hopefully, a little bit of sense. So remember, to take the derivative of a natural log, I take the derivative of what I take the natural log of. So I'm taking the derivative of the natural log of x squared. To take the derivative of that natural log, I have to take it 2x over x squared. So the derivative of the function, derivative of x squared is 2x, divided by that function. And I have to divide it by the function that I took the natural log of. Well, how does that end up looking like that? Well, let's play a little bit with this. We have x over x squared, so that's going to reduce to 2 over x over the natural log of x squared. Now I can go ahead, I have a fraction divided by something. I can do my multiplication by the reciprocal, and that's going to give me 2 over x natural logs of x squared. That's still not exact. Oh, what can I do with that? Recall exponent rules for natural logs. I can bring that exponent to the front. So I can have 2 over 2x natural logs of x. Now my 2's will cancel, won't they? So I get 1 over x natural log of x. Oh, you go ahead and see it there. So you can see, it doesn't matter how we attack that problem, we're still going to get that same answer. We still have to remember some of our exponential rules for logarithms, or some of our properties, either multiplication or that exponent rule. So either way, we get the same answer, and however you see it, go ahead and attack it that way. So good luck, enjoy, gives you some ideas of how to find the derivatives of natural logs and our exponential functions. If you have questions, let me know. Enjoy.